Hello everyone, and welcome to this explainer. Today, we are absolutely tackling Chapter 5 of your Class 10 Mathematics syllabus, Arithmetic Progressions. Now listen, I know the phrase arithmetic progression sounds like some heavy, intimidating mathematical jargon, but I am going to prove to you right now that you already intuitively understand the math we're about to learn. We use it every single day. My goal for this session is to take you from that basic, everyday intuition all the way to absolute conceptual mastery, so you can tackle any complex number pattern life or your exams throws at you with total confidence. Let's get into it. Imagine a simple wooden ladder, just like the one we've got right here. I want you to really notice the structure of the steps, or the rungs. Let's say the very bottom rung is 45 centimeters long. As you climb up, the rungs decrease in length uniformly. They shrink by exactly 2 centimeters for every single step you go up. So the next one is 43 centimeters, then 41, then 39, and so on. Do you see it? There is a fixed, highly predictable rhythm happening here. Or let's consider this fun activity straight from the chapter, the classic potato race. A competitor starts at a bucket, runs 5 meters to pick up the very first potato, and runs back. But here's the catch. For every single subsequent potato, it's placed exactly 3 meters further down the line. So the distance she actually has to run from the bucket to the potato goes from 5 meters to 8 meters to 11 meters. Again, it's a strict repetitive pattern. We are adding exactly 3 meters every single time. Okay, let's connect the dots. What do a physical wooden ladder, a school sports potato race, and your textbook's example of Reena's starting monthly salary of 8,000 rupees all have in common? Really think about it for a second. Whether we're talking about the length of a piece of wood, the distance run on a field, or the rupees hitting a bank account, they all follow one golden rule. The next step is just the current step, plus or minus a fixed, unchanging amount. And that, my friends, is exactly what an arithmetic progression is. We call it an AP for short. The formal mathematical definition tells us it's a list of numbers where each term is obtained by adding a fixed number to the preceding term, except for the first term, of course. Now, this fixed number is the absolute heart and soul of an AP. In math, we call it the common difference, and we represent it with a simple lowercase letter d. Let's ground this abstract idea using Reena's salary. Reena gets a starting salary of 8,000 rupees, with an annual increment, a raise, of 500 rupees. We denote the very first term of any AP with the letter A. So here, A equals 8,000. Our common difference, D, is the 500 rupees added each year. By year 2, she makes 8,000 plus 500, which is 8,500. By year 3, we just add another 500 to get 9,000. It's that simple. A is exactly where you start, and D is the exact size of the step you take. Now, arithmetic progressions basically come in 2 flavors, finite and infinite. Finite APs have a definitive endpoint. There's a final last term. Think of the heights of a specific group of students standing in an assembly line, from shortest to tallest. It ends with the tallest student, right? Infinite APs, on the other hand, just keep going forever. Like counting numbers, 1, 2, 3, 4, they literally never stop. There is no last term. Let's look at the core funda here with a quick logical breakdown. If our first term is A, the second term is obviously A plus D. For the third term, we take the previous term and add D again, giving us A plus 2D. For the fourth term, we add D one more time to get A plus 3D. Look closely. Do you see the pattern? For the fourth term, we only added 3 Ds. For the third term, we added 2 Ds. The multiplier for D is always exactly 1 less than the position of the term. Now, what is really amazing about what we just did is that we organically discovered one of the most important formulas in mathematics without even trying. The nth term, which we write as A subscript n, is simply the first term A plus n minus 1 steps of D. Please, whatever you do, don't just blindly memorize this formula. Understand it as a logical shortcut. If you want to find the 100th step on a staircase, you start at the beginning and you literally just take 99 steps. That's all this formula is saying. Let's test out our brand new logical shortcut on example 3 from your textbook. We need to find the 10th term of the AP, 2, 7, 12, and so on. Instead of counting on our fingers like we used to, we just identify our variables. Our first term, A, is 2. The common difference, D, is 7 minus 2, which is 5. We plug it right in. The 10th term is A plus 9 times D. That's 2 plus 9 times 5. Well, 9 times 5 is 45, plus our starting 2 gives us 47. Boom! Done in seconds. Excellent work so far. We can now instantly pinpoint any specific term anywhere in an arithmetic progression. But let me pose a completely new challenge to you. What if an exam question asks you not to find the 100th term, but to actually add up all the numbers from the first term all the way up to the 100th term? Doing that manually would take hours, and frankly, mathematicians are way too lazy for that kind of repetitive work. We are going to need a new tool. Enter the formula for the sum of the first n terms. Now, take a deep breath. I know this formula looks a bit bulky and intimidating on the screen. S equals n over 2 times the quantity 2a plus n minus 1 times d. But look really closely. Don't let it scare you. Inside those brackets, it is basically built entirely out of the exact same variables we've already mastered, n, a, and d. It's literally just a new way to arrange our old friends to calculate total sums. And this brings us to an even faster, more brilliant method. If you are dealing with a finite AP and the question is kind enough to actually give you the last term, which we denote as L, you can completely skip that bulky formula we just looked at. Just use this massive time saver instead. The sum equals n over 2 multiplied by the first term plus the last term. Remember this shortcut for sure. It's an incredibly elegant trick that will save you a ton of precious calculation time during your boards. Let's put this into practice right away with example 11. Find the sum of the first 22 terms of the AP, 8, 3, -2, and so on. Pay super close attention here, guys. The sequence is decreasing. That means our common difference d has to be negative. 3 minus 8 is -5. We plug n equals 22, a equals 8, and d equals -5 into our sum formula. S equals 22 over 2 times 16 plus 21 times -5. This simplifies down to 11 times -89. Giving us a final sum of -979. Never, ever drop those negative signs. That is exactly where this calculation usually trips students up. All right, let's step up to the masterclass section of the chapter. We are going to tackle the famous concrete steps problem from the optional exercises. Now, this one looks incredibly intimidating at first glance because it's essentially a 3D geometry problem mixed with an AP problem. We have a concrete terrace with 15 physical steps. We need to find the total volume of concrete required to build the entire structure. The secret to solving these terrifying word problems is simply breaking down the physical dimensions into clear, simple math. Every single step has a uniform length of 50 meters and a tread or depth of ½ meter. The only thing that changes is the height. The first step has a height of 1/4 meter. The second step is 2 times 1/4. The third is 3 times 1/4. And remember, the formula for the volume of a rectangular prism is just length times breadth times height. So let's write it out. The volume of concrete for step 1 is 1/4 times 1/2 times 50. Step 2 is 2/4 times 1/2 times 50. Step 3 is 3/4 times 1/2 times 50. If you actually calculate those numbers out, you'll realize they form a perfect, beautiful arithmetic progression. Once you extract your A and your D from these volumes, you can completely drop all the messy 3D geometry and just let the AP sum formula for n equals 15 do all the heavy lifting for you. That is the true power of APs, simplifying complex reality into predictable, solvable patterns. Before we officially wrap up this explainer, let's do one final rapid-fire knowledge check. Look at this AP straight from your textbook, 6, 3, 0, -3. I want you to mentally calculate the common difference D right now. Take a second. What is it? So the absolutely crucial point here is, did you say +3 or -3? The correct answer is -3. Remember the golden rule we talked about. Always subtract the previous term from the current term. You subtract the first term from the second term. So 3 minus 6 is -3. Never just subtract the smaller number from the bigger number. Keep that rule tucked safely in your back pocket, master those 2 core formulas we derived, and you will have absolute conceptual mastery over this entire chapter. But before I go, let me leave you with something to chew on. What happens if a pattern doesn't add the same number every time, but instead multiplies by the same number? Say a bacteria population doubling every single year. That's a whole different kind of progression, and honestly, it's how the real universe truly grows. But well, that is a story for another explainer. Thanks so much for joining me, and keep exploring.